Good morning. I am working on a project where I'm going to try to reject or confirm whether the Lorentz contraction of a wire turns electricity into magnetism. I've left this question alone for a couple of weeks. Just watch the Relativity notes 14 and 15 to get a review. So let's start by making a list of used. The magnetic force on a particle of charge Q is QV cross B. The electric force of on a particle of charge Q is QE, where B is the magnetic field and E is the electric field. The electric field from a uniformly charged wire, the magnitude of the electric field is equal to the linear charge density divided by 2 pi r, and the linear charge density is equal to the cross-sectional area of the wire times its volume charge density, and the volume charge density here is represented by the rho sub E, which is, let's see, A is the wire's cross-sectional area, R is the distance from the wire, Q sub E is the charge of the carrier, while rho sub E is the carrier charge the volume carrier density, carriers per unit volume, and the lambda is the carriers per unit length. Okay, I see an error in this one. We have the permittivity of free space is epsilon naught. Google gives these awful units. That is meters cubed on the bottom, kilograms on the bottom, seconds to the fourth on the top, amps, which is coulombs per second, coulomb squared, second squared. Sorry, amps is on top, so it's coulomb squared, second squared, which means these seconds squared can cancel with that, leaving a second squared. This gives us, let's separate out kilogram meters squared per second squared over here. And let's go ahead and put a coulomb in there, and that just leaves us with coulomb out here. We could refer to that as coulomb squared per joule or coulombs per volt. I think I like this one better, just coulombs per volt. Other units given for this in Eric Weisstein's World of Physics is 8.85 times 10 to the negative 12th farads per meter. And I realize now I did make a mistake. This is coulombs per voltmeter. And this would be joule meters. Coulomb squared per joule. Because I left out that cubed. Anyway, for now I'll just call it coulomb squared per kilogram meter cubed. And in the magnetic equation, the permeability of free space makes a shown. So let's just go ahead and click on here. This thing gives it in Webers per ampere per meter. It says equivalent units are newtons per ampere squared. However, it doesn't say whether that's equivalent units for Webers or equivalent units for permeability. Looking it up on Google, I see meter kilogram per second squared. Ampere is coulomb squared per second squared. Interestingly enough, the seconds just cancel out and you're left with kilogram meters per coulomb squared. Let's do one other thing. This is missing second squared up here, and now let's multiply those together. And this thing times this thing should come out to be second squared per meter squared. So, because 1 over the square root of mu sub naught, epsilon naught, is equal to the speed of light. That means my permittivity of free space needs to be coulomb squared second squared per kilogram meters cubed, and the permeability is kilogram meters per coulomb squared. Okay, the next thing I want to do is create a function, lambda of beta. Actually, it would look like more like this, but lambda naught is q sub e rho sub q times the area of wire, cross-sectional area. Beta is going to be the velocity of those charge carriers. Sorry, that should be an E. The velocity of the charge carriers divided by the speed of light. Now the unit length of the wire is going to be shortened by a factor of gamma. So L sub naught over gamma. But the or gamma of beta. But the charge carrier density is going to be multiplied lambda sub naught times gamma of beta. Now this gamma of beta is called a Lorentz contraction factor. It's going to be 1 over square root of 1 minus beta squared, also known as hyperbolic cosh of beta. No, I'm sorry. Cosh of phi, where phi is the hyperbolic arctangent of beta. That's not going to provide us any real simplification. The simplification that we're going to use is this, that beta is very small. So we're going to use something called a Maclaurin series expansion. And the Maclaurin series expansion is a sum, I believe, if I've got this right, it's of the derivatives of gamma, I should say, times, that's right, times beta to the, let's see, the derivative of this function at beta equals 0 of times beta to the I. Okay, so the first term would be the derivative, the 0th derivative of 1 minus square root of 1 minus beta squared at 0. The 0th derivative is 1 divided by square root of 1 minus 0 squared. Let's do the first derivative of 1 minus beta squared to the negative 1. That is equal to, let's see, we're going to take that to the first derivative. That's going to be negative 1 times 1 minus beta squared to the negative 2 times 2 beta. And we plug in beta equals 0 into that, and that will be equal to 0. Let's write that as, let's write down this first derivative. Whoa, I made a mistake. This is negative 1/2. This should not be negative 2, it should be negative 3. So I'm going to try to take the second derivative, which is the derivative of the first derivative, and so this, the derivative of the first part here is just negative 2 times 1 minus beta squared to the negative 3/2, plus the derivative of the second part, or plus negative 2 beta times the derivative of the second part, which is negative 3/2 times 1 minus beta squared to the negative 5/2 times 2b. So this will be 2b times 2b, 2 beta. In any case, all I care about right now is when plugging in beta equals 0. So everything after this is all cancels 0 when beta equals 0. And I think I introduced an error right around here when I didn't have that negative 1/2 in there. That should have been negative 1/2, and so this would be negative 1. So I would end up with, well, why don't I be honest with myself and say the chances of me getting this right by hand is very close, but the chances of Mathematica getting it right are quite a bit higher. Here is the derivative of 1 over square root of 1 minus beta squared. And here is the second derivative of that same thing. Here is the first derivative after we put in beta is 0. And this format is a /dot, escape beta gets 0. Actually, that's not really the way you would ordinarily write gets. That's backwards. Anyway, we've got 0 and 1 for the first and second derivative. So the first part of this is 1 plus 0 over 1 factorial times beta to the first. Actually, this is 1 times 1 over 0 factorial times beta to the 0. And then the last part is 1 over 2 factorial times beta squared. So with the first, second, and third derivatives in there, this expands to 1 plus beta squared over 2 and this is what 1 over square root of 1 minus beta squared over 1 minus beta squared is. So instead of calling this lambda of beta, I'm going to call this Lorentz contracted charge density. Lambda is equal to gamma times lambda sub naught, which is approximately 1 plus beta squared over 2 times lambda sub naught. Now let's look at the magnetic force equation, and this is the force of a charge going by, or the velocity of a charge going, and it tells what force is on that charge. So if I imagine a charge q going at velocity v, you can think of the wire consisting of several positive charge carriers and then the individual electrons going at a velocity of v, and the current is going this way. But that's not the convention we want to set up. We want to keep in mind that the magnetic field is mu sub naught I over 2 pi. So this QV cross B is also QV mu sub naught I over 2 pi r. And that current is going to be equal to the area times the drift velocity of the electron times the density, charge carrier density times the density of each electron, or the charge on each. So if we choose the convention that Q sub E is negative, then the velocity of the electrons is going to be opposite the current. So if we have a current going through this wire in this direction, the velocity of the electrons will be in that direction, or will be a negative number going. So we'll say V sub E is a negative number going to the. And our sign convention for current and the velocity of the electron will be the. We will go ahead and make the velocity of the charge also be the same direction, the velocity of the test charge. So basically we're making our sign convention be positive right. Now, from the perspective of the test charge, the positive charges will be traveling with magnitude velocity with magnitude v, and the negative charges will be traveling with velocity v minus v sub e. And since v sub e will be a negative number if they're going that way, v minus v sub e is actually going to be greater than v. And the electric force is charge times electric. And the electric field was lambda over 2 pi r, but here we're going to have two different sources, lambda of v and lambda of v minus. Lambda of v is going to be a positive charges, and we'll be subtracting lambda of v minus v sub e all over 2 pi r. But let's go ahead and replace those v's with beta. So it'll be lambda of beta minus lambda of beta minus beta of electron. Lambda of beta was 1 plus beta squared over 2 lambda, and lambda of beta minus beta sub e is just going to have that beta minus beta sub e squared. We can cancel out 1 and 1 and just be left beta squared minus beta minus beta sub e squared over 2 times lambda sub naught. So now I'll just expand out this part, which is beta squared minus 2 beta beta sub e plus beta sub e squared. The beta squared minus beta squared cancels. The beta sub e squared is very you'll find that the drift velocity of electrons in the system is extremely. So this leaves us with negative negative makes a positive, 2 over 2 makes 1, beta 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 epsilon beta e lambda naught. And it looks like I did not multiply by q here, so the force equals beta e lambda sub naught times. Another thing that I left out, and I keep doing this, is leaving out that epsilon naught, so let's put that epsilon naught on the bottom. And in fact, I didn't include that 2 pi r either. So this here was derived from the Lorentz contraction, and I want to compare it to the force of a magnetic field, which, let's see, we're going to take this current and fill in this. So it'll be Q sub E, Q sub E times V sub E times rho sub E A times mu sub naught 2 over 2 pi r. Now this Q sub E rho sub E is the charge density times the area is lambda sub naught. Then V sub E is going to be beta sub E times C squared. I'll go ahead and take this Q over 2 pi r, Q over 2 pi r, and this mu sub naught, put it right here next to the C squared, and look at that click. If it turns out that these equations are the same, B beta sub E lambda sub naught, Q 2 pi r, and the only difference is if C squared mu sub naught is equal to epsilon naught, then these are the same. Sorry, if C squared mu sub naught is equal to 1 over epsilon naught. And is it true that C squared equals 1 over mu sub naught epsilon naught? Is it true that C equals 1 over the square root of mu sub naught epsilon naught? Yes, it is. So actually, this does appear to confirm that the Lorentz contraction of a wire turns electricity into magnetic. So in summary, the magnetic force is force equals QV cross B. We replace that magnetic field with the magnetic field from a current carrying wire, which is mu sub naught I over 2 pi r. We also replace the current with Q sub E rho sub E A times the velocity of the electrons. And then we find that when we replace B with this and I with this, then we get QV mu sub naught Q rho sub E A V sub E over 2 pi r. Okay, now with the Lorentz effect, force is equal to charge times the electric field, where E is the electric field. We replace the E with lambda over 2 pi epsilon naught r. Since lambda p was 1 plus beta squared over 2, and lambda sub E was negative 1 plus beta minus beta sub E quantity squared over 2 lambda sub E, we can actually find the apparent total charge density to be, when you actually work these two things out and subtract them, you can actually get rid of everything except the beta sub E lambda sub naught, which is V sub E C squared lambda. When you then replace the lambda sub naught with q sub e rho sub e a, you get the final expanded form, which is pretty much the same as the final expanded form for the magnetic force. And in conclusion, with the final replacement of mu sub naught equals c squared over epsilon naught, this confirms that the magnetic field of a current carrying wire is the result of the differences Lorentz contraction of the charge. Just notice this is not quite right, and so I have a mistake in here when I was changing from beta to v and v sub e. Okay, that c squared should be on the bottom because beta equals v over c, and that c squared should be on the bottom, and this c squared should be on the bottom. So mu sub naught epsilon naught equals 1 over c. And this is something that I've been planning to do for a while. I'm glad I've got it done now.